Today we're going to talk about solving rational equations and inequalities. The equations shouldn't be too much trouble. I think we've done those before, but the inequalities gave us troubles when we were doing quadratics, and I assume they'll give us a little bit of trouble when we do rational inequalities. So let's start here. The best thing to do in most of these, since we're trying to isolate x and solve for x, is really eliminate any of the fractions. So what we're going to do is basically what we did freshman year is clear the fractions. That means finding a common denominator on all parts of each fraction and then multiplying every term in the equation on both sides by that LCD. So in this first case we have 5, 4, and 5. My LCD in this case will be a 20. So I'm going to multiply everything by 20. And when I do that, I distribute to each term. Now you'll notice this is 20 times x plus 3 over 5. I'll just write it out the first time so you can see. And that 20 and that 5 will reduce. This will be a common theme as we go throughout. So this is 20x over 4, and those will reduce. And this is 20 and x minus 2 over 5. So we reduce here and we get 4 times x plus 3. We get 5x. And we get 4 and x minus 2. Now it's just a simple linear equation with variables on both sides. We multiply through, so I have 4x plus 12 minus 5x equals 4x minus 8. The 4x's are going to reduce out, so I have 12 minus 5x equals negative 8. Bring the 12 over. Negative 5x equals negative 20, and x equals 4. Problem done. So as I said before, we're going to use that same theme throughout. I look at both sides of the equation, and remember over here we have an unwritten 1 as a denominator. So my LCD in this case is going to be x and x plus 2, and I'll multiply that to both sides of the equation. So in this first case, my x's will reduce, leaving me with an x plus 2. The second case, when I multiply over here, my x plus 2's will reduce, leaving me with an x squared. And in this third case, there's no reduction, so that's x times x plus 2. So now I combine like terms. There aren't any over here, so I have x squared plus x plus 2 is equal to x squared plus 2x. Get everything to one side since I have a quadratic. Well, actually those x squareds will reduce out, so I have x plus 2 is equal to 2x. Subtract x over, and 2 is equal to x. So in this case, I could multiply both sides by x squared minus 7x plus 10 and x minus 5, but I'd like to see first if there are any common factors. So I'm going to need to go ahead and factor first. So I have x minus 5, and sure enough there was a common factor, and x minus 2. So I have an LCD in this case of x minus 5 and x minus 2. I'll multiply each side by that. So in multiplying to the first term, both go. I'm left with 3. Second term, nothing goes. So in this case what I'll do is I'll just, since I'm going to have to FOIL this out anyways, I know it's just x squared minus 7x plus 10. And then in the last term, my x minus 5's reduce, and I have x minus 4 and x minus 2. So now I FOIL and distribute. That's 2x squared minus 14x plus 20. This is x squared minus, that's 2 and 4, which is 6x plus 8. since I have a quadratic, I set aside equal to 0, subtract the x over, and I have x squared. I have a 3. All right, let's go with the negative 14, add the 6 over, so that's a negative 8x. Then I have 23 and bring the 8 over, so that's going to be a 15. And that's actually a positive. So then I factor, that's x minus 3, x minus 5 is equal to 0. So x equals 3 and x equals 5. So now we're going to talk about inequalities. Typically in inequalities, what we're going to want to do is we're going to want to set aside equal to 0. This is already done for us. Now let's kind of keep in mind what's happening here. This is a rational function. And in a rational function, we're going to have asymptotes. This has a horizontal of 1, a vertical of 5, x-intercept of 0, y-intercept of 0, and I know this graph looks similar to this from what we've studied so far. Now we want to know when this graph is less than 0. Now some interesting things happen in rational functions. We know that whenever we hit an axis, there's a possibility of something going from positive to negative, and when we hit an axis, we know that the y value equals 0. But then, typically, when we cross an asymptote, in terms of a vertical asymptote, not necessarily a horizontal asymptote, but in terms of a vertical asymptote, something new could happen to the function. That function could go from a negative value to a positive value, but it could also go from negative and stay negative. So we know important things happen at intercepts in terms of the x, and at vertical asymptotes, or when denominator equals 0. Okay, so in this case, I've set aside equal to 0. I know I have a vertical asymptote at x equals 5, and I know I have an x-intercept at 0. So what I'm going to do is I'm going to go back to a number line and look at those two, what we call, these are called critical numbers. And we're going to test what happens to either side of these numbers. And we've done this before with quadratics, like I said. So I'm going to take a look at some values of what happens when the function equals -1, what happens when the function is 1, and what happens when the function is 6. And if you look after plugging into the equation, I have a negative on top and a negative on bottom. So to the left of 0, as we can see here, we have a positive value. When I look at 1, I have a positive over a negative, which equals a negative. So to the right of 0, I have a negative. And then when I go to the right of 5, I have a positive over a positive, which is a positive. All right. And to the right of 5, I have a positive value. This is asking, when is my function going to be less than or equal to 0? So that's in between 0 and 5. However, at 0, we can be equal to 0 since that's an intercept. So 0 is greater than or equal to x, but my function can't be equal to 5 because I have an asymptote there, so it's just strictly less than 5. And this is my solution. If I were to put that on a number line, we know that what that looks like. Circle at 0, open circle at 5, and then I'm done. So now we want to take, and first thing we want to do is set aside equal to 0. In doing that, it doesn't really matter which side you set equal to 0. I'm going to go this way, subtract the 2 over x plus 2. And then I'm going to try to simplify that expression so it would look like something I would graph. I have an LCD in this case of x minus 3 and x plus 2. So in this case, this is 3 times x plus 2 minus 2 times x minus 3 over x minus 3 x plus 2 greater than 0. Next I want to simplify. I have 3x plus 6 minus 2x plus 6 over that LCD term. So that gives me x plus 12 over x minus 3 and x plus 2. So now we're ready to get going in terms of finding intercepts and where the denominator equals 0. So denominator equals 0 at x equaling negative 2 and 3, and the x-intercept ends up being negative 12. So what I'll do now is I'll set up my number line looking at negative 12, negative 2, and positive 3, and then test my intervals around these numbers. So test at 4, 0, negative 5, and negative 15. And I'm going to plug all these numbers into this equation down here. So when I plug in a positive 4, I get a positive over 2 positives, which is a positive. When I plug in a 0, I get a positive over a negative and a positive, which is a negative. When I plug in a negative 5, I get a positive over a negative and a negative, which is a positive. When I plug in a negative 15, I get a negative over 2 more negatives, which ends up being a negative. And what I'm looking for is values that are greater than 0, which means that my positive numbers. So my solutions in this case, since they're all going to be greater than and none of them can be equal to, I'm going to use just the inequality of greater than for my answer. So I need the answers between negative 12 and 2. So I say negative 12 is less than x, which is less than negative 2. And then I also need the numbers greater than 3. Since I have 2 pieces of my answer that need to be linked, I write or in between, and I'm done. Let's do a couple more examples. Again, we're going to set aside equal to 0. So in this case, I have 1 over 3x plus 2 over 9x minus 2/3 less than 0. LCD in this case is 9x. So I will change my denominator to 9x. This first term needs a multiplication of a 3. Second term needs nothing. Third term needs a multiplication of a 3x. So cleaning it up, I have 5 minus 6x over 9x is less than 0. So again, I'll look at my vertical asymptote numbers, which will create a critical number. That's x equals 0. And then an x-intercept type number, that's going to be 5, 6 is equal to x, and then I'll test these points. So again, I'm going to look at 0 and 5, 6 and check values around those. So we'll look at -1. How about a half? And 1. Plugging -1 in to this term here, I'm going to get a positive over a negative, which is a negative. Plugging a half in, that gives me a positive over a positive, which is a positive. And then plugging 1 in, I get a negative over a positive, which is a negative. And I'm looking for values that are less than 0. So that's this one here and this one here. So that tells me it's all the numbers less than 0. And then it tells me it's all the numbers, all the numbers x that are greater than 5, 6. And since these are not necessarily connected, like so, then what I have is I have an OR problem. Last example. Again, set that side equal to 0. We have 5x over x plus 2 plus 2 over x minus 5 over 1 less than 0. LCD in this case is x and x plus 2. I create that LCD of x and x plus 2. Change my numerator. I notice that first term is missing an x, so that's 5x squared. The second term is missing an x plus 2, so that's 2 times x plus 2. And then that last term is missing both, so that's minus 5. And then x times x plus 2, less than 0. Clean it up. We have 5x squared plus 2x plus 4 minus 5x squared minus 10x over x times x plus 2 is less than 0. 5x squareds go away. I'm left with negative 8x plus 4 over x times x plus 2 is less than 0. So I would take and find those vertical asymptotes, or the numbers that set the denominator equal to 0. That gives me a 0 and a negative 2. And then the intercept is going to equal a half. Check some points. I'm looking at negative 2, 0, and a half. So the points I'm going to need to look at are negative 3, negative 1, about a quarter, and 2, what the heck. So when I plug in a negative 3, I end up with a positive over 2 negatives, which is a positive. Plugging in a negative 1, I have a positive again over a negative and a positive, which is a negative. Plugging in a quarter, I have a positive over 2 positives, which is a positive. And plugging in 2, I have a negative over 2 positives, which is a negative, which means that the values that are less than 0 are all my negative values right here, So I have the values between -2 and 0, as well as those values that are greater than 1/2. And I put an or in between since they aren't linked together. If I wanted to graph that, I'd have a -2, open circle, another open circle at 0, and then at 1/2 I'd have an open circle with an arrow going to the right. And there's my solution. That's all we've got. Make sure you fill out your summary and do your Connect Ed, and we'll talk to you tomorrow.